Now that you know how to take the derivative of the exponential function, the natural exponential function, we need to look at how do I take the derivative of the natural logarithmic function. So when I take the derivative of ln of x, it is going to be a formula similar to when I take the derivative of sine of x or cosine of x or e to the x. The derivative of ln of x is 1 over x. I have to make sure that whenever I use logarithms, I'm always going to be greater than 0, because if you remember, this is what the graph of the natural logarithmic function looks like. So notice this domain restriction here comes from the fact that the logarithmic function does have this vertical asymptote and does not ever use any of our negative x values. So let's look at some examples where we are differentiating our natural logarithmic function. Just like with the natural exponential function, we do have to watch for chain rules, product rules, quotient rules, things like that. I do have 5 examples. The 5th one is probably the most important example. So please do make sure that you watch all the way, either all the way through to the 5th example, or once you feel like you've understanding it, that you fast forward through to watch the 5th example. But let's start with our first example, A. So when I differentiate the natural logarithm of 2x, I notice that my inside function here, I'm taking the derivative, or excuse me, I'm taking the natural log of this linear function, so I am going to have use the chain rule. So I'm going to let u equal 2x and v equal ln of u. U prime is then 2 and v prime is 1 over u. So u prime times v prime gives me 2 over u. U is 2x, which the 2's reduce, and I'm left with 1 over x. From there, I'm going to move on to example B. I do apologize if you can hear the background noise. But looking at example B, I'm going to go ahead and I'm going to notice that it's very similar to example A in the aspect that I'm taking ln of x squared plus 1. So again, that prompts me to use my chain rule. So I'm going to go ahead and let u equal x squared plus 1. And then u prime is 2x. I'm going to let v equal ln of u, and then v prime would then be 1 over u. So multiplying u prime times v prime, I get 2x over u, which I designated to be x squared plus 1. Unlike the first example, there isn't anything I can do to reduce here, so I'm going to go ahead and leave it like that and move on to example C. On letter C, notice that I have the derivative of x times ln of x, which prompts me to use my product rule. So I'm going to go ahead and say my first function is x, and the derivative of my first function is 1. My second function is ln of x, and the derivative of my second function is then 1 over x. Remember, the product rule tells me to take the derivative of the first times the second plus the derivative of the second times the first. My plus is kind of funky. So the derivative of the first times the second gives me 1 times ln of x, so that gives me just ln of x, plus the derivative of the second times the first, so 1 over x times x, which is going to be x over x, or just 1. So I get a final answer of ln of x plus 1. Moving on to letter D, I notice I have ln of x cubed, so that implies that I have an inside function and an outside function. So I'm going to go ahead and move my screen a little bit. I'm going to go ahead and let u be ln of x, since that's the thing that is being cubed, and v be u cubed. U prime is then 1 over x. V prime is then 3u squared. So taking u prime times v prime, I get 3 over x times ln of x squared for my derivative. And now looking at that 5th example that I wanted to make sure that everyone made sure to watch, I noticed that I have a ton going on in this problem. I see that I have multiplication, I see that I have something being squared, so chain rule, product rule, and also have division, so quotient rule. So I might at first be slightly intimidated by this, because I think that it's going to take me a very long time to accomplish the problem. However, after looking at it a little bit closer, I realized that I can expand this, and then I'm not going to have to try to squish so many rules together. So using my rules for my logarithms, I'm going to first take and say that if I'm dividing inside of a logarithmic function, I can separate that into a subtraction between two logarithmic functions. So I'm going to have ln of x times x plus 1 squared minus ln of the square root of 2x cubed minus 1. And now I'm going to notice that if I have multiplication between two functions, I can go ahead and create two new logarithmic functions that are adding and have ln of x plus ln of x plus 1 squared minus ln, and I'm going to go ahead and put this to the 1/2 power. You'll see why in a moment. And now I'm going to go ahead and say, hey, I know that if logarithmic functions have a quantity that's being raised to a power, I can bring that power out to the front, giving me ln of x plus 2 times ln of x plus 1 minus 1/2 ln of 2x cubed minus 1. Please keep in mind that I have not done any differentiating yet. I've just done some work to now get ready to differentiate. This front term is going to be no problem to differentiate. It's just going to be 1 over x. However, my second and third term both involve inside functions, so I am going to have to use a chain rule on each of those. So in my second function, I'm going to let u equal x plus 1 and v equal 2 ln of u. U prime then equals 1 and v prime then equals 2 over u, or 2 times 1 over u. On my third term, doing the same thing, I'm going to let u equal 2x cubed minus 1, v equal 1/2 ln of u. U prime then is 6x squared. V prime is then 1/2 times 1 over u, so I'm going to say 1 over 2u. And now I'm going to go ahead and use those to aid me in differentiating this piece here. So once again, as I said before, that ln of x just becomes 1 over x plus u prime times v prime, so 1 times 2 over u, so 2 over x plus 1 minus my u prime times v prime, so minus, I'm going to say 6x squared over 2 times 2x cubed minus 1. I am going to reduce my 6 and my 2. I'm not going to get a common denominator. I could get a common denominator. My least common denominator, keep in mind, would be x times x plus 1 times 2x cubed minus 1. Notice I'm not including the 2 because I am going to, as I said just a moment ago, reduce it with that 6. And then multiply all of my tops by the appropriate, I guess, piece of the denominator to get that common denominator. But that gives me 1 over x, just canceling again. Oops, that's a subtract. And as I said just a moment ago, I could get a common denominator. I don't think I'm going to here. If you would like to see how that would be done, please make sure and let me know, and I can go through that with you in class.